Good afternoon or good morning, depending on where it is that you're joining us today. Very pleased to have you with us on this web seminar about additive manufacturing, state-of-the-art inspection methods and powder analysis. My name is Stephen Ward and I'm going to host the session today, which means I'm just going to introduce the speakers and get out of the way as quickly as I can, and then I'll come back at the end to host the Q&A that we'll have at the end of the session. Okay, let's move on into our session then. So this is the structure for what we're going to do today. I'm very pleased to be joined in the room here in Cambridge by two of my colleagues, Dr. Donna Dykeman, who is the manager of the collaborative R&D function here at Granta. If you want to say hello, Donna.
Hello everyone, looking forward to addressing you today with some of the outcomes of the AMAZE project.
That's great. And Najib Baig is here too. Najib is manager of our additive manufacturing technology here, product manager of that technology here at Granta, and towards the end of the seminar he's going to show us some of that technology and how it's used for managing materials information. If you want to say hello, Najib.
Hello, good morning, good afternoon, wherever you're dialing in from. Happy to see so many people, and I look forward to presenting later on.
And then on the line from the Manufacturing Technology Centre, which is some miles from here in England, near Coventry, we have our guest speakers today who we're really pleased to have with us. So that's Dr. Ben Dutton. Ben is a principal research engineer at the MTC, and Jason Dawes. Jason is technology manager at the MTC, and they're going to talk to us about key technologies in additive manufacturing, as you see here on the screen, non-destructive testing standards, and how we really understand the use of powders in additive manufacturing. So just to check we can hear you, Ben and Jason, if you want to unmute yourselves and say hello, that would be great.
Yeah, hello and welcome everybody. This is Ben Dutton. I'll be presenting right after Donna.
Hello, this is Jason Dawes. So good morning, good afternoon to everyone. So I'll be presenting after Ben on understanding powders for additive manufacturing.
Terrific. Well, thank you guys. Thank you very much. We'll come back to you shortly, but as you see on the agenda here, we'll move straight into that without any further ado. We're going to kick it off by Donna talking a little bit about the AMAZE project, and she'll tell you what that is and some of the challenges that came out of that project and some of the interesting work that's resulted. So I'll hand over to you, Donna.
That's great. So thank you very much, Steve. And the title of the slides that we're going to cover is the challenges and solutions for qualifying larger AM parts, some of the outcomes from the AMAZE project. And the purpose of the next few slides is to give you a bit of an overview of the AMAZE project, some of its purposes and the challenges that it addressed. It by no means today in this webinar are we going to be able to talk about all of the outcomes of AMAZE. This is really just a snapshot of some of the work that Granta and MTC worked on. But we're going to come back to this point at the end of the webinar and share some resources to help you find out more information and connect with more partners. So just to give you an introduction to AMAZE, this acronym has been around for several years now, and really what it stands for is Additive Manufacturing, aiming towards zero waste and efficient production of high-tech metal parts. This is the largest and most ambitious metal additive manufacturing research project in Europe, which was funded to the level of 18 million euros on behalf of the European Union, the Framework 7 program specifically. And because this was focused on demonstrations, it was funded also in part by industry. The project was 4.5 years long, so that started December 13th, and we just closed it off in June 2017 with an open forum that was held at the MTC. So the AMAZE partnership consists of 26 organizations across Europe. And I'm just going to flick to the next slide while I talk about the partnership so you can have a chance to absorb exactly who was present. So AMAZE brought together a representation, we would say, of the leading institutes and enterprises in Europe for additive manufacturing. So to start with, there's a good presence of research technology organizations and universities who worked with partners on fundamental research problems, as well as how to translate these solutions to industry use. So secondly, we were well represented by world-leading end users who brought their business cases and their challenges to the consortia, and they represented the aerospace, the space, automotive, and energy sectors. Thirdly, we had a strong supply chain representation from designers, software developers, machine manufacturers, post-processing, NDT and metrology, and fixturing. So some of the major metal AM technologies that were underpinning the research included technologies such as the wire and arc additive manufacturing technique, or WAM as it's known as, rapid plasma deposition, blown powder deposition, laser metal deposition, wire feed laser beam process, laser powder fusion, and direct energy deposition, as well as selective laser melting. So the project aims overall could be summarized in four short statements, although there's a lot of work that is going into each of these statements. So they are increasing the build rate of AM processing, extending part size and complexity, improving part quality, particularly by the reduction of defects and scrap, and widening the range of proven materials for additive manufacturing. Now, in the next few slides, I've added also some pictures that we took of parts and of consortium members, and this one is highlighting a 6-meter WAM part that was made by Cranfield University as part of the outcomes for the work that they did in AMAZE. So the benefits of additive manufacturing really don't need to be widely explained today, given the work that's been done globally on this topic over the past decade. And they are widely acknowledged as being geometrical freedom, production flexibility, efficient use of materials, and material freedom. And I'm just showing another couple of the demonstration use cases that came out of AMAZE. So one is the Thales satellite sun sensor, which was originally made of 3 tubes and was designed for geometrical efficiency, reducing the amount of material by about 52%. And so there was very significant environmental and cost impacts that followed on from those decisions. The other one I'm showing here was made by the UK Atomic Energy Association, and it's a copper and vanadium component, both of which are typically difficult by additive manufacturing, but they came up with a way to do that, and what it gives them is a lot of flexibility in the field. But also these materials are particularly needed in their harsh environment in the energy sector. So just to move on, some of the barriers to introduction of AM for production that were highlighted by our partners even at the onset of the project, and these are what we aim to address. So one is the limited range of proven materials and associated mechanical property data. And we'll touch on this a bit more, and certainly there is data out there which we have as product offerings, but the industry as a whole acknowledges that there's a lot more work to be done to get qualification level data available to industry. We would say probably still a poor understanding of opportunities and requirements for design for AM. Obviously not all parts are AM applicable, and there's also a lot of value add in terms of the finishing applications and also the repair applications that AM can offer. Limited knowledge of fundamental principles which underpin the AM process. There was a lot of work done in the project looking at the melt process that was measuring and also modeling it, and that's very important for being able to improve your resource efficiency and improve your feeds and speeds. Another part of this knowledge base, though, is what's happening with your feedstock material. And so that's what we have the MTC here to talk about today. And this is something that obviously the quality that comes in is going to be reflected in your part quality at the end as well. And this important part shouldn't be forgotten. So finally, given those barriers above, I think it's fairly self-evident that a lack of industrial case studies to demonstrate the process benefits and limitations are available in the public literature today. And so AMAZE really targeted that opportunity, and it looked at 15 different use case studies where parts were designed and produced. So the AMAZE objectives overall were to produce large AM metallic components, to have an increase in process productivity, to reduce defect scrap levels, reduce cost of finishing parts, and improve in-process and ex-situ inspection methods. And I'm just showing another part down here below a pylon bracket. It actually underwent laser polishing, which was developed in the project, and it also underwent some more design optimization techniques as well. So the scope of the project was structured around these limitations that the industry had brought to us as a challenge, and also the critical objectives that I talked about earlier. And really the result was the development of a robust end-to-end additive manufacturing process chain. And so just to list out those components of the process chain, they are part design for AM, materials research, high productivity AM process development, process modeling, process monitoring and control, finishing of parts, final inspection, developing integrated and streamlined AM factory solutions. And so what we're going to talk now today for the rest of this session is some of the outcomes that were developed by the MTC and Granta, and how they overlapped onto some of this end-to-end AM process chain. Certainly in the materials research area, the feedstock characterization and control for qualification work that the MTC has done, as well as NDT and metrology applications, whether that's for process monitoring or for final part inspection. And for Granta's part, we hosted a centralized materials data management database for the project, which is not only taking a look at an industrial level application of materials information to support factory solutions, but was also there to capture all the information through that end-to-end process chain for the project, and that's going to have a life after the project, which we're going to talk about as well. So at this point, I'm going to pass it back to Steve, who's going to
That's great.
manage the next stage.
Thank you very much, Donna. So I'm going to just turn it over to our next presenter, who is Ben Dutton at MTC. So hopefully, Ben, you're now able to share your slides with us. That's great. I can see them starting to come up here. And just while Ben is getting his slides on the screen, let me remind everybody that if you have any questions at any point, so for example, if you have any questions based on what Donna has just presented, put them to me as the meeting host on the chat, and I will collect them and we'll answer them at the end of the seminar session today. So I see your slides here, Ben. Can we let's just check we can hear you.
Yeah, can you hear me?
Yes, we can. Great. So over to you.
Okay, great. Thank you. Thank you, Steve and Donna. Yeah, so I'm going to be presenting basically some highlights, actually, from mainly from AMAZE, how it contributes to the development of NDT standards for additive manufacturing. Just to begin, I'll start with a quick introduction of the MTC and basically the background. We opened in 2011. It's an independent RTO, Research Technology Organization. And the main objective is to bridge the valley of death, which means we have a lot of very good research from universities, and we're struggling basically to get into the industry. So we want to basically bridge that gap, and also improve and innovate manufacturing ideas and produce manufacturing solutions for them. And in addition to that, we do training, which at the end we'll show you some one slide on that. The MTC is divided into three, as you see, three main large groups, which includes, as you see, additive manufacturing, for instance, non-conventional machining, high-intensity fabrication. That's for the component manufacturing. Then we have assembly systems, which includes advanced tooling and fixturing. We got electronics, a big group on electronics manufacturing. We also have robotics and automation systems. And the last one at the bottom, we got data systems. And there we have design and simulation. We have a nice VR room and other equipment related to that. We have informatics, manufacturing. And where I personally sit is in the metrology and NDT, as the last one on the bottom right. And about additive manufacture, we do quite a bit here at the MTC. We're the home of the National Center for AM, and we have an end-to-end capability, and from design, powder characterization, and fully finished high-integrity components. We are risk-free independent environment, which means we're not tied to any particular company, basically. We are a member-based company, and but we are independent, and that's one of the advantages that we have. We can give free advice to, which is not tied to any particular company. So just a bit more now into the group which I belong, metrology NDT. My background is NDT, and what I'll be talking now is about NDT, and we have quite a variety of expertise and project brochures and that we cover. Now, right into the actual subject, which is the NDT standards for additive manufacturing. Additive manufacture is a great tool and a way to design very complex features or parts, as you see some examples there, and there are even more complex lattices, very lattice sections designs. But for NDT, that is a headache basically. So there is this particular, or particularly the freedom of geometry, and added to the roughness of the finished parts are causing challenges to the NDT. So therefore, there's a need to improve the NDT, or to have novel NDT basically. Some of the main areas that, from our knowledge, that they require standards is aerospace, automotive, and medical. There are others which also do, but also remains what we believe. And there's a number of international efforts producing such standards, and a big one is the one that I'm leading. I'll be presenting here. I will be mentioning another one that are also participating. So the standard which I'm leading is a big long name, as you see on the top. It's basically a joint effort between ISO and ASTM, and our activities goes through BSI, the British Standards Institute, and basically the standard is going to be coming out from both ISO and ASTM, as I understand, and I'm the convener, as I say, and this is a best practice guide as we are starting it to define it, because that's something that we typically do when you don't have a very, very defined, let's say, method to inspect a very defined part. Let's say AM is so complex, and therefore NDT methods can vary quite widely. So it's a guide which basically represents potential potential and then tested NDT methods to detect defects which are not covered by current standards. I will explain what that means by not covered by current standards. And it covers both post-build and in-process NDT. The first draft has been generated and been submitted and approved as a project, and the aim for the final submission will be around December next year. A couple of slides on the types of defects which we have actually firstly generated mainly from research projects at the MTC, and most of them also from AMAZE basically. So these are some of the defects that we find only believe in additive manufacturing. So these are typical powder bed fusion defects. Some of them are electron beam melting, and some of them are laser powder bed fusion. But mainly, this is to highlight that those type of defects, for instance, cross-layer defects, those images you see there, X-rays, X-ray CT, those are just slides of the X-ray CT. It's a vertical cut up on the left, and the top of the build layer slice, just to show the morphology of the defects, which typically don't occur in the other method, basically. Then you got layer defects, and we also have powder bed, trap powder and unconsolidated powder. Trap powder basically is a powder that, for the geometry that it was designed, the powder gets trapped. And it may or may not be a problem, and therefore we may need to detect it. Then the difference on consolidated powder is the powder that you meant to melt, but for some reason, some process errors, or you just didn't do that. Now, in direct energy deposition, this is some of the examples here that the types of defects that occur. You got typically poor surface finish, then you got porosity, then you have, but then on top of that, it typically undercuts because of the size of the beads typically, and you could have incomplete fusion and cracking. So the progress of this standard has been, this is a timeline of both the past, present, past, present, and future, basically. So the past, we have mainly started with a MACE project, and then followed up with a CRP, a core research project here at the MTC. And then AMAZE also provided at the end some support, and then you can see there the different tasks that we have on each of the steps of there, and then what we proposed on the coming on this year and the coming years to actually finalize the standard. So more detail into the scope and the definition of the standard that we are using is that we look basically at the types of defects that additive manufacture generates in both powder bed fusion and direct energy deposition. And then, but we reviewed current standards, and mainly we reviewed welding and casting. Welding has a similarity to direct energy deposition, and therefore we also saw that it has similarities of defects. So we believe most of the defects from DED can be covered by most of the current welding standards. Now, powder bed fusion has some more unique defects, which when compared to casting, for instance, we believe some of them can be covered by current standards, provided obviously we can validate them, and but also considering the finish of the part and the geometry, which typically in casting cannot be that complex. And then you have the very unique defects, which we need very specific standards. So the structure of this standard is as you see in this slide. So depending on the part, the level of quality required, and acceptance level, some of defects or some of the defects can be covered by the current standards, which is the blue sections. For the defects, obviously depending on the acceptance requirements and so on, some of the defects will need new NDT standards, and those will be the new standards that will be developed. This, apologies for the size, I don't know if you can read that. I just could have fit it all in here, but this is something that will be included in the standards, and this is a table showing the potential of NDT methods for each of those unique additive manufacture defects. And the size of that green bar is the estimated potential for detecting that particular defect for using a particular NDT method. Now, this we made it an estimate, which we could actually modify the roughness of the sample. In this case, is the worst case. So typically, electron beam melting is rougher than laser powder bed, and also geometrical complexity. So here we put the worst case that we believe it is lattice structures. So this is the worst case scenario basically. But it's a matrix which we generated also for our maze, and it's something that can be depending on the level of porosity, or not porosity, I'm sorry, surface roughness and geometrical complexity. It'll give you different outputs. Now, for the standard, we have created an artifact, as you see there. And this is we're covering the post-built NDT section, and we decided a somewhat complex, but at least also areas that we can actually define with different kinds of defects. So in some of the areas we have horizontal cylinders, and then we got our vertical cylinders. So those were seated, mimicking the types of defects which are layer defects or cross-layer defects vertically. And then we got spheres, which is basically trap powder, and then we also have cylinders, which are trap powder at different angles. We define this. This design is dependent on the material because we're trying to optimize for X-ray CT, basically with a 10% transmission. And then we have, those are the actual builds that we have done, one for Inconel and one for titanium. We have a number of those artifacts, and the sizes are relative. It is the true proportion basically. So titanium would be actually larger because it's less dense. So because of the rule that we're following for 10% transmission. And then next I'm going to show you just one example because otherwise I would take several hours just showing you some of the results that we have, and some will include in the standard. This is X-ray CT, different projections of the artifacts which were scanned. There were 1, 2, 3, 4 stacked stars basically, as you see on the top right stacks, and then the 3D image on the bottom right, and then just a slice of where those vertical cylinders were concatenated, and we can see that the 3 largest ones were easily detectable. The one about 200 microns, it started to get more faint. But we have also cut up some of those, and that 200 microns is much better detailed than you see here, and that's due to the limitation of the X-ray CT resolution. So that 200 microns, what's possible to do, it's just not as clear as in here, basically. And some other thing that I'm highlighting is the X-ray CT has some of the difficulties, let's say, is the artifacts. In this case, I'm showing artifacts due to the scattering of the sample. This is a very dense part, which makes it these artifacts more visible. The other thing that we are also considering in the standard is that we have these artifacts, but perhaps or most of the cases, well, depending on the geometry, it will not be representative for that particular part that you're building. So for those cases, the recommendation is to create we call it a la carte artifact, which is closer or very close to what the geometry you'll be building. And this is thanks to one of the partners that's working with us, and GE Alstom, GE Power, and this is a part which is not it's not confidential, and it's not the geometry they are actually going to build, but it's representative to what they actually would like to test, basically. So we have built that, and we have also X-ray CT. I will not go into those details, but this is just to show that the standard is assessing that level of complexity that obviously will occur in AM. Then just a couple of slides on in-process NDT, which was developed during the AMAZE project. This is the same part that Donna showed, and yeah, it's called output 3, but it's the Thales part. This is an aluminum part which was built, but in this case, it's showing the process was not under control, which in some way is good for NDT, because we like to see defects and then test if the method the NDT method is capable. So the first test on the top is a crack, or in this case, it's a surface defect, which is a layer defect, because that's along the build layer. So it's an opening surface crack, and we basically scan with laser ultrasound, and just before and after that defect, as you can see my mouse, basically this was the generation laser and this was the detection laser, and both of them move along this direction. So it's moving downwards in this here. So this is it's called a B scan, which is a stack of the A scans with ultrasound basically generates. And we can see the surface Rayleigh wave here very clearly, and then some of the effect of that crack. This is to show, or basically starting to show the capability of laser ultrasound, perhaps for in-process inspection, although we are doing it for a part. But the principle here is that this is as built, so we haven't machined it, we haven't polished, we haven't done anything to the part, so it's as rough as it is. Then we did another scan in an area which I marked here, which has no visible defects, but from the X-ray, which I don't have time to show you, but the X-ray CT shows at least two defects which are here around this area, and that's the reason I chose this area to scan. So the same, we have the same setup here, and then both lasers were scanned in this direction, and this is the corresponding B scan. So this is showing, these dimensions are not from the laser ultrasound, but from X-ray CT. There were a couple of voids. In this case, was about 200 microns, and I would say about because obviously our system is not perfectly calibrated, but those are just ballpark values. But we can see this disturbance of the ultrasound signal on both cases. So it's showing capability for that. The other example I want to show you, also from the AMAZE project, is that this is a plasma transfer arc, I believe, system with a wire fed, and there are basically at least two beads here in parallel that were deposited, and I asked for the sample to have representative defects, and so they told me there were sections with basically some black effusion between the beads. So what I'm showing you here is again the B scan. This is the direction of the scan basically. So one laser was on one of the beads, the other laser was on more or less on the peak of that other bead. And here's the B scan of that. And this actually are no, it's correct, yeah, from 0. So the scanning is from top to bottom, and so this area here has a large effect on the delay in the Rayleigh. This is the surface Rayleigh wave, but there are also some features here which are, I believe, due to deeper defects, which I presume they are from possibly porosity or lack of fusion between the top and bottom beads, or top bead and the plate. And this is to show a large difference of when there's a defect and when there's no defect on the A scan, basically. So this laser ultrasound system is showing capability for both powder bed and for the potential for in-process, basically. So, in general, the contributions of AMAZE for these standards are the joint group which I'm leading, which is the NPs for new project 52905, and it's a joint group 59. But also, I'm participating and the types of defects were used on the ASTM work group is E07, and that's the work group number. Obviously, it's also the AMAZE has been useful to review the possibility methods and the process as I just showed you, and obviously also some disseminations as you see at the bottom. So in conclusion, we have MTC has been leading the development of entity standards, and through ISO and ASTM, and a lot of has been due to the advantage of working with this AMAZE project. But more, I believe that more effort and ideally joint effort is required to provide what this industry or those sectors urgently require. And without entity standards, well, there are obvious difficulties of certifying and verifying the parts, and it's quite an issue. And the challenge for NDT is that we require novel methods and to cover both post-build and in-process. And actually, in-process may have a potential to reduce or eliminate post-build inspection. At least that would be the best solution or the goal to go for. And so, in addition to novel methods, perhaps improving the existing ones would be the solution. Yeah, I think that's all I have. So I'll hand it over to Jason now.
That's great. Thank you very much, Ben. Just to remind people, if you have questions, do send them in on the chat to me as the meeting host. I'll turn it over to you, Jason. If it's possible to get through this in 5 to 10 minutes, that would be terrific, and we'll have time to hand over to Najib then. Thank you.
Okay, thanks. I'll do my best to bring this in for 10 minutes. So I'm going to give you an overview. It'll be a whistle-stop tour by the sounds of it of some of the work and developments that took place with respect to powder analysis and powder inspection that was done within AMAZE. I think one of the biggest things for me to say here is probably myself and perhaps other people that work within the MTC. I mean, we take it for granted, the level of analysis that we do, but I think as Donna mentioned at the start, the AMAZE project was 4.5 years. So, 4.5 years ago, there were a lot of questions being asked within AMAZE and within the wider sort of industrial base that MTC were working with, is what is the best way to analyse powders, and what are the right things to be measuring. So hopefully this gives you a good overview of the background to where a lot of the analysis techniques we do today is where they came from. So just 3 sort of areas I want to touch on in this presentation. So I want to talk a little bit about importance of powder characteristics in AM. So why is it that we care so much about powder for AM applications? A little bit about powder specifications. So one of the big activities in AMAZE was in developing specifications by which we would order materials for AM applications. And then I'm able to share just a small case study which shows an example of how we analyze the supply chain for titanium 6-4 powder, and give you an overview of how we sort of down selected from those 4 suppliers a batch that we used within AMAZE. So I like to split the importance of powder for AM into 2 sort of categories, one looking at commercial and one looking at technical. So commercially, if you consider titanium 6-4, it can cost in the order of around 1/3 of the production. That's taken into account how much it costs to run the machines, the power requirements for the machines, the whole process. Traditionally, up to about 1/3 can come directly from your powder. Because your powder is such a major cost of the process, in order to make the business economical, you have to be able to reuse the material. So you're probably all aware that AM is a process in which you build parts additively, and it's called very near net shape. The reality is that you end up with a component potentially that's maybe 15, 20 kilos, but in order to make that component, you may have actually used 200 kilograms of powder. So that leaves you with a sizable amount of powder, which if you can't use that again, then clearly the economics of the business case doesn't work. Another point is the supply chain needs to be validated. So there are a many number of ways in which you can make metal powder, but there are even more places that you can buy your powder from. One of the sort of favoured methods, I guess, for supply chain in additive is directly through machine platform providers. So, for example, if I buy an electron beam melting machine, an EBM machine made by Arcam, I would typically go to Arcam and buy my powder from Arcam. However, the issue with that, of course, is if you're not directly in control of your supply chain, you don't necessarily know where your AM, equipment providers are getting their material from, what you open yourself up to. And this is something that has happened in the past to us, is that those suppliers of the powders, they can change their source where they get the powder from. And so if you don't understand what in the first place makes a good powder, if you're not in control of your supply chain, and then things like that do happen where things get switched around, then you're not necessarily going to be guaranteeing product quality. On the technical side of things, because you're making components layer by layer, you can typically, in an EBM machine, for instance, spread several thousand layers of powder. The issue with that, of course, is that gives you 1,000 chances to get it wrong. So a lot of the defects that Ben mentioned, you've got several thousand chances to introduce those defects. So you've got to make sure that powder is consistent for every single layer you spread. Because I mentioned commercially you have to be able to reuse the powder, you need to therefore manage powder change through multiple use. So there's a classic issue with titanium, for example, where the more times you use it, the more oxygen you pick up. Eventually you will pick up too much oxygen, you'll be out of spec. So you've got to be able to understand how to manage the reuse of powder in the AM process. And then, of course, you've got the old adage where quality of powder directly impacts part quality. So, you put rubbish powder in, you're going to get a rubbish product out. So in terms of the EBM process or an SLM process, I've just got a generic image on the slide at the moment that just gives you an overview of what an AM machine looks like in a very simple terms. And if you look at the different stages of the process, you can start to understand where powder starts to impact. So firstly, you've got powder storage. In this scenario, bulk density becomes important, because obviously the lower the bulk density, the less material you can store, or the bigger container you're going to need to store the powder in. Moisture content, because that could cause bridging in the hopper. And then particle size distribution, so ideally you'd want it to be no segregation, so you've got the same, from top to bottom, you've got the same distribution. At some stage you need to dose your powder from that hopper into a dosing unit. So then I'm interested in powder flow. So will my material reliably flow from my storage hopper in front of my spreader? Will I get the same amount every time? Again, particle size distribution, will I be seeing any kind of segregation, which could give me varying part property from bottom to top? I then need to spread that dose powder. So again, what I care about now is how easily will my powder flow. Will it lock up and not spread efficiently? Will it be too free flowing and spread too much? What I want is a very nice uniform flow of powder across the build table. Again, particle size distribution, and again, moisture content, because that's the kind of thing that's going to start to affect how it flows. Then when I actually want to melt the material, so now I care about the chemistry. So have I got the correct chemistry? Is my powder clean? Do I have any particulates in there that are foreign to the bulk? They're going to cause me inclusion issues. Porosity, so how densely packed is that powder bed, and bulk density. So in terms of powder quality, how do we define powder quality? So I like to say there's 4 things that you might want to measure about powder quality. So firstly, you've got your particulate properties. So in this case, we're interested in particle size, particle morphology, porosity. So how much are my solid particles, are they solid, or do they have entrapped air in them? And of course, we're interested in the metallurgy of the particles. You've then got your bulk packing and flow. So in this case, we're interested in how those particles in assembly, how they flow in a bulk scenario. So do they flow well? Do they pack well? Then you've got your chemistry. So bulk alloy composition. So titanium 6-4, for instance, do I have the right composition of vanadium and aluminium? But also interstitial elements, so do I have the right composition of oxygen, for instance? And then paired cleanliness is much harder to define how you measure paired cleanliness, but as an AM user, using paired potentially 50, 100 times, how many times you use it, how clean is it? Does it stay clean? Am I picking up debris from the equipment that it goes through? Am I picking up cross-contamination? So we know what we want to measure, but what are the right properties, or what do we think are the right properties for an AM paired? So firstly, you're never going to choose your AM paired based on how it flows or how it packs. The first thing is the chemistry right? So any AM paired we order, first thing you want to check is you've got to get the right chemistry. Correct particle size fraction is probably the next most important. So depending on what AM method I'm using, I have very distinct size fractions. So for instance, laser paired bed fusion traditionally would use 15 to 45 microns. Electron beam, melting because of the way it works, has something slightly larger. I've already mentioned flow, so ability to spread evenly. Flow is a very challenging thing to measure. I suppose today we still don't have potentially a very accurate way of measuring spreadability of powder, so that's an area for future development. We can get a good understanding of how easily it will flow from a dosing unit, but in terms of how it spreads. Consistent ball packing density, so generally speaking, again, we don't know how to measure this in situ, but generally speaking, we want the highest packing density we can get. To get the above properties, generally speaking, you want a spherical morphology. So they're sort of technical things, but then also you've got the commercial things. So affordability, is my powder cost effective? And does my supplier who I go to, does he have the correct capacity in order to meet my requirements? So without wanting to dwell on this area too much, the challenge that exists, as I mentioned in an earlier slide, is that there are many ways in which we can make powder. Fortunately, based on what we think we need for AM, there are only a few of those, like plasma atomized and gas atomized methods, which are suitable. Other methods don't make the right kind of paired properties or are just cost prohibitive. So I've got a few slides that I can run through reasonably quickly that go into a case study looking at 4 suppliers of titanium 6-4, which was used for an electron beam melting application. So nominal size would be 45 to 106 microns. So the first thing we want to look at is morphology. So we can do this in a number of ways. On the slide now is showing you a comparison of SEM images of the 4 suppliers. When we're looking at morphology, like I mentioned, ideally we want spherical particles. What we want to be avoiding is some of the examples shown in the top left there is things like the splat caps and the elongated and broken agglomerated particles. They're the kind of particles that are going to start to form effectively interlocking. So they're going to reduce our level of packing, and they're going to prevent our ability for the powder to flow and to spread in the dosing unit. Another issue is satellite. So fine particles will again impede flow, but also they become a health and safety risk. So some of the satellites you see can be much, much finer than the bulk. So typically speaking, you can get sort of 5 to 10 microns, and they then start to pose safety risks. So if we look at the 4 suppliers here, again, they're completely anonymized, so you can't see who they are. But generally speaking, we can start to make some assertions about which powder batches would be best. In this case, generally speaking, morphology at least, they're all quite acceptable, but some hit that level of sphericity better than others. So supplier 1 and 3 in this case, we say, well, they're really ideal. They're very highly spherical, very low satellites, very low agglomerations. Supplier 2 and 4, we can accept that morphology, but it's not as ideal. Next, we want to look at something like particle size. So generally speaking, there are multiple methods that you would use to measure particle size. So you would use sieve analysis combined with something like a laser diffraction. This graph shows some results from a laser diffraction methodology. Some of the things we would be typically looking for is adherence to that size fraction. So does the bulk of the distribution lie in 45 to 106? Is my material monomodally distributed, like all 4 are in this case? Is it Gaussianly distributed? Again, all 4 are. What we can take from this chart is that supplier 4, for whatever instant reason, seems to have a higher proportion of coarse. That in itself is not necessarily an issue. Of course, we can post-treat this powder and take that coarse material out. We can sieve it, classify it in another way. But of course, that starts to affect yield. And what affects yield starts to affect then cost of the powder. So the next thing we want to look at is chemistry. So I've just generically picked out oxygen here for titanium 6-4. Obviously, oxygen is quite important. Now, the first thing to point out here is this would be a grade 25, a standard titanium grade. So your specification for the part is somewhat higher. It would be 0.2. But of course, because this is a powder, what we need to ensure is that when we're specifying powders, we're not actually buying it on the limit of the chemistry spec. We want to be buying it some way below, so we can then use it multiple times. The issue we have if we're just ordering against the standard spec is whether it's 0.14, whether it's 0.2, it's still in spec. Problem is I can't use the 0.2 very many times before it goes out of spec. So when we're specifying AM powder, we generally want to go to a much lower. So perhaps when you're buying in titanium 6-4, you might want to go to the ELI grade, the extra low interstitial. That gives you a quite good margin in which to pick up oxygen in the process. In this case, we find that supplier free, and it seems to be something more unique with that particular powder, powder production method. Supplier free seems to be very much exceeding the oxygen limit. Is even on the limit of the standard grade titanium 6-4. So for AM purposes, this is much too high. We look at flow. So in this scenario, we use a classic traditional methodology called Hall flow. In this scenario, all 4 suppliers were within what we specified as ideal flow for AM. Then the final thing we looked at was apparent density. In this case, we can see, probably quite linked to morphology, suppliers 1 and 3 tend to have the highest packing density, suppliers 2 and 4 somewhat lower. Suppliers 2 and 4 just peeking into the specification limit, but supplier 1 and 3, because obviously what we're saying is higher is better, more favourable from that perspective. In terms of what we do with all of that data, we then try to score and try and define which is the best material or the most suitable. We have the technical things, which is around your morphology, your PSD, your chemistry, etc. But of course, there's also the commercial things. So within a maze, some of the things that we were looking at were cost. Is it cost effective? But also location. So not all of these suppliers were European-based. So some suppliers would have scored higher because of the fact that we're European-based rather than other areas of the world. So generally speaking, once you've got multiple suppliers, you want to specify it against both technical, so that's all the properties, but also the commercial. In this case, supplier 2 was selected as the preferred supplier to the Amaze program, and we continue to work with supplier 2 for the duration of the project. Of course, any new materials they sent, obviously this is a snapshot of batches, so any new materials they submitted to the Amaze consortium, we reran through the test to make sure they were still in the right limits. So just in summary there, so some of the things that we've been doing with the Amaze powder specification is trying to address the critical KPVs for powders. So again, 4.5 years ago, I don't think it was well known what those KPVs are. I think today we have a much better handle on what the right type of powders are for AM. We did a good down selection of European-wide and worldwide suppliers of powders and assess their ability to adhere to desired properties. And again, like I mentioned, all of the information was, all of the powders that were in the future put into Amaze, we checked for compliance against that spec. And then I think Najib will be talking about this, but all of the information we generated as part of the Amaze project on all of this powder information was uploaded into the Amaze database, which is a database controlled by Granta. So I think Najib should have some interesting things to say about that as well. So in terms of the content of the slide, that's everything Ben and I had to talk about. So I think from that we can pass.
That's great. Thank you very much, Jason. A very good segue there at the end to Najib, who is indeed going to talk to us briefly about some of the information management aspects of the project and the technology that was used to do that. So I'll hand over to you, Najib, and as soon as Najib's finished, we'll take questions about the whole content of the seminar.
Okay, perfect. Thank you very much, Jason and Ben. That was excellent. So I'll be talking about information management for additive manufacturing. That's one of the key challenges for additive certification and standardization, which is ultimately the end goal that everyone wants to achieve. And this is a very information-intensive process where a lot of information is being generated. So the key challenge we want to address is how do we manage all that information? And this was realized as a critical requirement and challenge as part of the MAZE project, as you heard from Jason and Ben and Donna. But it's also important for our materials data management consortia members that include these OEMs that you can see on the slide, as well as other customer projects that we're working at to help solve these challenges. So I'm going to give you a quick demonstration for a solution for managing all the different steps in the additive manufacturing process. So if we start with powders, so relating that to Jason's presentation, there's a lot of materials characterization data generated in the process. And it's absolutely critical to ensure that you are capturing all those information. So here in front of you, you can see we are managing and capturing some basic information on your powder materials, the mass, supplier information, number of containers, anything that's important in terms of inventory management. Of course, the critical powder properties that you want to capture, material quality. Jason mentioned recycling of powder materials are an important aspect, so you need to keep track on that. Chemical analysis, and also capturing to what test method those were captured. Now we can also capture blended powder materials, which is done quite often. So here you can see the powder properties and chemical analysis for these two different batch of powder that were blended together. And it's very important to keep traceability of your information. So from powders, you can follow all the builds that was manufactured using that powder. So we're capturing all the critical information for the build, such as the drawing file, STL file, all the test data, tensile test relating to Ben's presentation, the non-destructive testing that was carried out on the build, parameter settings for the machine, powder used in process information, as well as any post-processing done on your part. Looking at CD scans as an example of test data capture, we're capturing all the critical information. We have the summary image captured on the porosity. We also have more detailed image analysis in terms of defect size distribution, CT scan parameters. It's also quite critical to capture sensor information from your machines, and I'll show you one example of doing that for a Renishaw log file. And you can automate this process, which a lot of our customers do, and select the format depending on which machine manufacturers you have, ranging from Orcam, EOS to Renishaw. We do support most of them. We can go ahead and extract the log information, that is the sensor information from the machine, and we can have a look at that information within the system with easy access and analysis. So we can have a look at, so this is the record, and this is the information extracted from the log file. So we're looking at all the critical parameters, user settings, layer height profiles, laser temperature profiles, chamber temperature profiles, pressure, basically any type of sensor information you want to capture about your machines, whether that's EOS, Renishaw, SLM. That's absolutely critical that you ensure that you are capturing that information. Once you have the information managed and captured and traceable, it's equally important to analyze that information, understand and optimize your process parameters. This is one example of where we're looking at a plot on the position on the build, so x-axis position versus the y position, and you can see the coloring here is the number of defects, so we can quickly identify where do we have the most defects in our build, so we can quickly understand and qualify our parts. Here's another example where we're looking at the number of recycling against oxygen contamination as well as nitrogen contamination. And finally, here's one assessment of a process parameter travel speed, and see the effect on ultimate tensile strength. And we can see the optimal travel speed is 10.5 to gain the highest UTS value. Okay, so as part of the MAZE project, what was used was the Granta MI Additive Manufacturing package that allows you to capture your project data, ensure you have traceability, analysis, capability on your data, support you in certification, and allow you to have a accurate business process for additive manufacturing, as with any other business process that you have within your organization. Okay, I'll hand over to Donna to conclude.
Okay.
Yes.
Thank you so much, Najib, and I'm really just going to take a couple minutes just to make some summary statements and make some acknowledgements, because we're keen to get on to the question period, and we realize we've run over time a little bit. So for Granta, the AMAZE project was an incredible opportunity to be working in additive manufacturing when it was really just starting to kick off and being adopted more widely. It gave us a great advantage commercially, in that we were able to come up with the world's first accepted schema for additive manufacturing. So as Najib was just taking you through a little bit of a whistle-stop tour in our database today, all of those attributes and the links between the tables and how that's organized is our schema. And so that was tested by our partners, that's been tested by the Materials Data Management Consortia and by our customers, and that continues to grow. So something else that is a big outcome for us is the ongoing collaboration, and I'm sure that MTC can attest to this as well. So one thing that we are trying to do is to make sure that the data captured in AMAZE has a life after the project. The project has ended, and we have formed an exploitation board, and we are looking for more opportunities to grow that through public funding. So if you have an interest in that and you're within a European zone, please do come and talk to us about that. There's a strong AM community and supply chain engagement as a result of this project for all partners, and we certainly felt that. In terms of some of the solutions that we worked on with the partners, again, Najib talked a little bit about the tools, the analysis tools that we have. We really looked at the end-to-end solution for materials data management for additive manufacturing, and we'd be happy to talk to you more about that. So in terms of further resources, now that the project is closed, there is a lot of information available. And so I just wanted to direct you very quickly to the website, the handbook from the Open Forum Day, where we had one day full of presentations. Those presentations are available on the website as well. And some are available on YouTube. So you can actually hear Jason giving a more extensive conversation about the work that they did on characterization on YouTube. And of course, I want to direct you as well to the solution that we've developed here at Granta for additive manufacturing. So in acknowledgement, certainly we just want to emphasize again that this wouldn't have been possible without the funding of the European Union. This is a great opportunity for countries in Europe to come together and develop solutions together, and really you don't have this opportunity very often because of the proprietary nature of the work. We want to thank all of the AMAZE partners, which we were happy to show their logos today, and if you want to learn more about them, reach out to them, do go to the AMAZE website. And of course to the coordinators of the AMAZE project, David Wimpany from the MTC over the past year and a half, and David Jarvis, who was working for ESA, now works for Metallurgy Europe, started that project in its initial stage and took us to 2016.
Great, thank you very much. Well, I think we've come to the end of the presentation material, so we're going to move into a Q&A session very quickly now. Just a few pieces of contact information here if you have further questions after the webinar. Here's some suggestions for who to discuss for the different aspects we've talked about. Now, as I said at the outset, we will send a copy of these slides around to everybody who is registered for this webinar. We'll do that in the next day or two, so you'll have all the slides that Grant has presented, and that will include this one, with these contact details on them. So if you have questions regarding services and leadership in AM, feedstock control and NDT, then you could get in touch with Ben and Jason, or various aspects of Granta's work with Donna, or the software you saw demonstrated with Najib. And if you are in our locality, if you're in the UK or within easy plane ride of where we are, it might be worth pointing out that we have a seminar that we're running about materials information technology, actually at the MTC in early November, and that's open for registration right now, so you may want to go to that link, take a look and see if you could spare the day to join us. We'd love to see you. So let's move into the questions. I know a lot of people will be dropping off now. They maybe have booked an hour with us today. So if you need to do that, thank you for the time you have spent with us. Do look out for the email with the slides in it, and do get in touch with your questions if you didn't have a chance to have them answered right now. We'll take maybe 10 minutes or so for those of you who are able to stay with us, just to dip into some of the questions here. We've had a great audience today, I must say. This is a very interesting topic to the community. Clearly, we've had well over 200 people on the webinar today, so we don't have time to answer all the questions in 10 minutes. I'm going to pick 3 or 4 for each of our speakers, and hopefully we have the questions from other people, and we'll maybe be able to follow up with you after the session to make sure we answer them. So Ben, if you're there, maybe you could take a couple of questions, if we just check we can hear you.
Yeah. Have you selected any questions, or you want me to?
Yeah, no, I'll go here. I've got, let me maybe pick 3 from the list that have been sent in to you. So the first one is the standards that you were referring to. How applicable are they to space applications?
Yeah, the standards I'm developing is basically it can cover many sectors basically, so it's not dependent to a specific sector, and so it's not for sentencing the part basically, but it's a guide to start showing the capability of NDT methods to find defects that are required to be found in additive manufacturing. So it's quite generic, so it's not really dependent to a sector.
Okay, that's great. That's clear, I think. And someone here says regarding the NDT standard which is being drafted, and they apologise that they missed the reference number, but I guess it'll be maybe in the slides if we're able to distribute those after the meeting. Does it include both powder and wire-based processes?
There are some some differences and some similarities, but I believe they're talking about direct ion deposition, and at the moment we have been done mostly on wire, but it really can cover both. It's not limited to either one.
Okay, that's great. And somebody commented that the defects you showed reminded them of the ones you can find for welding, and they wondered whether how they defects were influenced by the speed or the power of the process.
Yeah, about how the process affects defects, I'm not an expert in that area, so that I couldn't answer. But the other part, which is the similarities, that is what we're exploiting in this. We are reviewing standards for welding and also for casting, which they also have. So for welding, there are a lot of similarities, more similarities than for casting, and we're taking advantage of that very close similarity to static defects. We believe the DED is typically or mostly covered by those, but obviously there may be some final very fine differences. On casting, there are also some similarities, but there are some which they do not exist in casting when you compare to powder bed. So that's what we have found. Yes.
Okay, that's great. Thanks. Maybe a couple of questions for you, Jason, if I may.
course.
Somebody pointing out that you listed metallurgy as a powder property separate from chemical composition. So they're wondering what you mean by metallurgy in this context.
Okay, so one of the things that we tend to do is we would mount the paired particles in resin and then polish through. So we look at cross sections of the paired particles. So some of the things we'll be looking at is the microstructure of the powder and trying to understand, is there any cross through or transfer of the, depending on the powder metallurgy, does that affect then the part metallurgy? I think in AM it tends to be, because you're melting it, you don't tend to see that follow through of metallurgy, but we know in some of the other powder metallurgy processes like hot isostatic pressing or cold isostatic pressing, you certainly see effect of the starting microstructure of the powder particles, and you see that effect then in the final part. But some of the other things that we're looking for is segregations. So maybe not so much with the titaniums, but with some of the nickel superalloys, that we'd be looking for certain, segregations of certain alloys, certain alloying elements. And then we're looking at porosity as well within the same sort of suite of analysis. So that's what I mean by the metallurgy of the powder particles.
Okay, that's great, thank you. This question was asked, maybe you did address it later, but somebody was wondering why you weren't looking at the thermal properties of the powders.
The thermal properties in terms of how they melt, it's not something that we've specifically looked into at the MTC. So I couldn't really comment on what the methodology would be. I mean, some of the things that we're looking towards at the moment are things like differential scanning calorimetry and thermogravimetrical analysis, so trying to look at melting points and trying to find out if you can see the effect of contamination in powder batches. So you see multiple melt peaks, for instance, and trying to understand if the effect of oxygen pickup has any effect on that. That's some of the stuff we'll be looking to do in the future, but to date, no, we haven't looked at thermal characteristics.
Okay, that's fine. I've got a few questions about the LU scanning method, actually. Things like what's the accuracy of the method for porosity detection, but also just a kind of general question, really, of how can I find out more information about LU scanning?
So you mean laser ultrasound, no? Do you refer to laser ultrasound? Is that right?
Sorry, yes. Yes.
Yeah, sure. Yeah. Well, it's a very I would say complex system. Let's say you need a lot of background. But I'm by the way, I'm an expert in that area, so that's why we're using it here. But it has tremendous potential, basically. But the difference between let's compare, for instance, if you know about conventional ultrasound. Conventional ultrasound is a probe which can be a single element or array or so on, but it has a very narrow bandwidth, basically. Conversely, the laser ultrasound has wide band, so you have that much more information because it's a very quick impulse, basically, that generates the ultrasound. And then you have also the advantage that in laser ultrasound you create all the modes at the same time. You got surface waves, bulk waves, and in comparison with contact ultrasound, you have a single mode depending on how the probe is oriented, basically. So, but the advantage also, additional advantage of laser ultrasound is that you have a totally non-contact method because it's totally optical in both generation and detection. So it's potentially very useful for high temperature or when you have you want to avoid contamination, which usually, for instance, contact ultrasound would do. And so it's there are several industrial applications, and but we believe for AM there is a great potential to be exploited, basically.
Okay, that's great. Then maybe just to wrap up, got a couple of questions here for Najib. The first one is what different types of powder materials can you manage with the system?
Okay,
With
thank you.
Granta MI, I guess, is the...
Yeah, sure. No, that's a good question. So really, you can manage any type of material, whether that's titanium alloy, nickel, steel. The system is capable of controlling and managing any type of material, essentially. So that's not a problem.
So somebody else asking, can the database be used for SLS with polymers? Would the answer be? What would the answer be there?
Yes, certainly could be used for SLS as well. As I mentioned earlier in the presentation, we do cover sort of out of the box with most of the key additive manufacturers and technology. So certainly we can support that process and materials as well.
Yeah. Okay. And then there's a question which I think the questioner then responded to say you actually had answered this question during your presentation, but it's maybe just worth asking it again just to clarify. How he was asking how the extremely large file sizes of data from in-process monitoring could be handled in concert with the MI system.
That's another very good question. So there are different approaches for handling that challenge. You can certainly, with the database, store that information and relate that to your summary data sheet that I showed early on, but that would be kept in a separate part of the database. But certainly that's something that could be supported by the system. Okay.
Great. I think we'll wrap up at that point. So thank you for staying with us through the Q&A. Hope that was an informative session for you. We, as I said a couple of times early on, do look out for the email with the link to the slides, and you'll then have the contact details that are here on the screen if you have more specific things to follow up. Apologies that we weren't able to answer all of the questions that came through. We'll go through those, and we may be able to respond directly to some of the questioners if we have your contact details. But don't hesitate to get in touch with us again through these mechanisms if you want to make sure you get an answer. I'd just like to thank you all for spending time with us, and particularly to thank you, Ben and Jason, for coming along and being our guest speakers today. That was most informative, and I think I'm getting messages on the chat saying thank you to everybody for the great webinar. So thanks for your contribution.
No, thank you. It was a great pleasure to us.
Yeah, thanks for inviting us to speak. Yeah.
Great. Okay. So with that, we'll wind up and wish you a great rest of the day, and look forward possibly to speaking to you again at a future Granta web seminar. Thank you very much.